Hello and welcome. Media Circuits was recently asked to present a tutorial on Amplifier Additive Phase Noise testing at the 2025 Low-Level RF Workshop in Newport News, Virginia, and hosted by the Thomas Jefferson National Accelerator facility. The talk was very well received, so we thought it would be nice to share it with our friends in the microwave community. So that's what we will do today. As we've done in the past, we'll go through our test set. We'll go through some additive phase noise theory. We're going to look at small signal, of course, but more importantly, large signal behavior. We're going to look at how AM to PM distortion could influence your additive phase noise performance. And we're going to look at some cascade design examples, not in depth, but just give you some examples of things to watch for. So to start, we'll go through our test set. And before we get into the actual block diagram we use the Roden-Schwarz FSWP for all of our measurements. I thought this is a nice way to show sort of the evolution of the measurements and the evolution of the phase detector. And I'm sure we remember back in the day, we all had our double balance mixer, maybe a NARDA microwave line stretcher to establish quadrature. We would try and lock our reference to the DUT, uncorrelated noise comes out, and hopefully it's representative of the DUT. So to improve upon that, a correlation type receiver was introduced. So now the uncorrelated noise is compared and anything not common is canceled. And that helped get a much better measurement than one could achieve with just a single channel. Then later on, the double balance mixers were replaced with IQ mixers. And this was nice because it allowed us to now look at additive amplitude and additive phase distortion essentially simultaneously by just doubling up on the digital channels. And then again, you have the most recent simplified block diagram for the FSWP showing the A to D converters and some of the processing that goes on. This is our test lab. As you can see, it's located in our class 100,000 clean room. Everything is positioned on a vibration isolated table. And you may notice that everything in addition to that has some type of vibration absorbing material under it. Be very careful about external vibrations influencing your measurement. The AC power for the analyzer is filtered and conditioned. We have very short RF cables running into this EMI enclosure. This is an EMI tight enclosure inside of which the amplifier or the device under test resides. We also have 3 SMA cables bringing DC voltages into the EMI tight enclosure, again, for better shielding. We don't want external noise perturbing our measurement. So that's the setup. The clean room ensures that we have very tightly controlled temperature and humidity, and works very well. I'm going to go into this apparatus on the front end in just a moment. So again, just repeating what I said, I'm not going to repeat it all, but I do want to stress that you must exert extreme care when you're tightening or torquing the RF SMA cables. If you twist the cable and leave that mechanical energy stored in the cable, it could be released as a microphase perturbation, or worst case, as a phase pop. So you want to try and make sure that the cable is not under torsional stress as you torque the ends of the SMA cable. And again, don't touch anything. So I want to focus on this, and you'll understand more as we go through the presentation as to why we spend so much time emphasizing the front end of our instrumentation. What we'll do is we will set the signal source output power to a very specific power level at each carrier frequency. The output power is not arbitrary. We identify, as you'll see later, the best power for that particular carrier frequency. Once that is established, we don't touch it. Any change in power level into the DUT results from changing either this fixed pad or this 1 dB, 11 dB range mechanical step attenuator. If we need more than 11 dB, we simply change the fixed pad and proceed. We want to make sure that we can drive the amplifier from small signal, large signal into saturation. Then on the output side, we have a similar arrangement because we want to keep the power back into the FSWP as consistent as possible. So we'll choose a power level that's consistent with the amplifier under test, somewhere ideally between plus 7 dBm and plus 13 dBm. And then we try and maintain that level throughout the duration of the testing to within about plus or minus 1 dB. And that makes sure that everything is more consistent and very repeatable. So again, I'm not going to repeat this. This is essentially what I just said. Emphasis on this output power level. Somewhere within that range, we pick something for that amplifier, and then we try and maintain it to about plus or minus 1 dB. Just some key settings that we use to configure our FSWP. Again, plus 13 happens to be the maximum that we can output from our instrument. It doesn't necessarily represent the best power level for all frequencies. We identify what that is, and you'll see how we do that shortly. And then again, we try and maintain the level back into the instrument at a very specific power level. So we're going to go into a little bit, what is amplifier additive phase noise? And we're going to focus on these two plots here, courtesy of Professor Rubiola. They look simple, but there's actually a tremendous amount of information contained within these two plots. First thing I want to define is what we have: white and flicker noise. Amplifiers will add two types of noise: white and flicker. White, the noise sidebands are independent of the carrier. We've all seen thermal noise, right? We all turned on spectrum analyzers and seen that noise floor. The carrier comes in fine, but it doesn't, the sidebands are not a function, okay, of the carrier. Flicker noise is very different. That's a parametric noise. What that means is it needs a carrier. Okay, so in the amplifier itself has this 1/F or this flicker noise present within it, but you cannot visually observe it until you pass a carrier through the amplifier. Then that low frequency flicker noise is parametrically upconverted to the carrier and appears as sidebands. So dependent upon carrier, not dependent upon carrier. Additive, flicker. What are these two plots? What is SRF of F? That's your spectrum analyzer. For the purposes of this conversation, that is our spectrum analyzer. We've all used spectrum analyzers. We set the center frequency to the carrier frequency of interest. We set the span, the amplitude, the resolution bandwidth. We take our amplifier, we connect the output of the amplifier to the input of the spectrum analyzer, and for right now, we just terminate the input of the amplifier. We've all done this, right? What do you see? You see white noise, right? You see the white noise that's there, affected by the choice of your resolution bandwidth will affect the level, but it's white noise. Then let's turn the amplifier on. What happens? You watch that white noise go up. It goes up by the gain and noise figure of the amplifier. You're now looking at the output noise power of your amplifier. Based on the gain and noise figure, that input noise will go up by that amount. Then we put a carrier in. We take a lab synthesizer, we insert the output of the synthesizer into the input of the amplifier, and we slowly start turning up the input power. What do we see? Right, we see the carrier start to emerge from the noise, and as it emerges further and further above the noise, we see sidebands. But we associate those sidebands with the absolute phase noise of the synthesizer that's being used. Now, let's change that lab synthesizer to, say, an ideal synthesizer, an impulse, something that has no sidebands per se, no absolute sidebands. And you do the same experiment. You vary the input power, you watch it come out of the noise, and as that signal emerges from the noise, you see sidebands. Those sidebands are a result of the amplifier's baseband noise, this 1/F, this flicker noise, being parametrically upconverted to that carrier. And that's what we're seeing here. What is S phi of F? S phi of F is the power spectral density of the random phase. In this with this terminology, the units are rad squared per hertz or rad squared second. We don't typically use those units in the microwave community, but that's what they are here. And this is like what you'd get from your phase noise analyzer. F in this case is the Fourier frequency, or for our discussion, the offset frequency from the carrier. And again, S sub phi is the power spectral density of the random phase. And now you can see the two components associated with the amplifier, the flicker, which is characterized by the flicker noise coefficient, which is B sub -1. And I want to stress that is a constant. For the small signal case that we're discussing now, that does not change. That is a constant. So this intersection of the flicker noise with, say, the 10 hertz axis, that does not change. It's a constant value that can be measured, obviously. It can also be determined theoretically. Once that value is known, the rate of change of the flicker noise with offset frequency is proportional to 1/f, or 10 dB per decade. So again, you have a constant that intersects an offset at a specific value, doesn't change. Go above or below that, the change is 10 dB per decade. As we go up, you'll see that it'll eventually intersect with this B0 term. B0 is the power spectral density in the white noise region. And there's a lot more going on than one would expect just looking at this simple equation. First of all, you can see lower power, I have higher noise. Higher power, I have lower noise. Look at the term FKT over P0. Look at F over P0. What you're seeing here is the signal to noise ratio, right? As your P0, your input power increases, the signal to noise ratio improves. As the signal power goes down, your signal to noise ratio decreases. That's what's going on here. So this has to be understood because there's a lot of emphasis, and I think incorrectly placed, on specifying the noise figure of the amplifier for best additive phase noise. Well, if I want the best, I can just increase my input power. So if I have a 1 dB noise figure and I put in 0 dBm, or if I have a 3 dB noise figure and I put in plus 2 dBm, I'm going to get the same thing here. All right, that needs to be understood. That noise figure is important, but input power is just as important because it's what's establishing your signal to noise ratio in the white noise region. So again, what is S? We discussed. What is L? L is what our instrumentation returns. Okay, we all call it additive phase noise. According to the IEEE, L with units of rad squared per hertz is simply 1/2 of the power spectral density in the same units, rad squared per hertz. But we typically never use those units. What we would do is express S as a dB. So we have dB rad squared hertz, and we express L as dBc per hertz. And in this case, for our amplifiers under consideration, dBc can be referred to dB below carrier. And again, the F can be considered offset frequency from carrier. And with that definition, you can see it's just a log of S minus 3 dB. Very straightforward, almost like measuring mass. I can measure mass in pounds or kilograms. It's still mass. Okay, so I can express it as S or L. It's still phase noise. The instrumentation that we use returns L, so we're going to work in terms of L. Why do we care? Why do we care about additive phase noise? Well, a number of reasons. At the Particle Accelerator conference that we were just at, the jitter is extremely important. And you can see here, because the timing of these RF cavities is very critical. So in the Particle Accelerator community, there's a lot of emphasis placed on reducing timing jitter. If we're doing communications, we all know that phase noise rotates the constellation, increases our bit error rate. So we all know about that. We know that we can integrate the area underneath the phase noise curve, and we can use that to compute the jitter We can use that to compute the maximum signal-to-noise ratio that is achievable with that phase noise. And something else that perhaps is not as obvious, but as we go through this, you'll see why it's important. If this is your oscillator and you pass it through an amplifier, that amplifier has the potential to degrade the absolute phase noise of your oscillator. And that's what we want to avoid. And that can occur by using the wrong amplifier, the wrong technology, or it can be done by operating the correct amplifier in the wrong region. So that's why we need to study small and large signal cases, because we don't want to spend all this money, have a really nice absolute phase noise source, and then destroy that performance by incorrectly operating the amplifier that precedes it. And also, just interestingly enough, the 1/F noise of the active device that's used in the oscillator, for example, will be mapped to that absolute phase noise. So the 1/F noise gets mapped to a 30 dB per decade, and the white noise gets mapped to a 20 dB per decade. So even if you're designing the oscillator, you need to be concerned about this, because it will affect the absolute phase noise. We won't get into that in this talk, though. So again, let's go back to white noise. And I'll try throughout the talk to kind of relate phase noise theory with some standard microwave cascade analysis theory. And we've seen this curve before, proportional to F over input power. P0 is the input power. And if you do cascade analysis, you're aware of a term called the MDS, the minimum discernible signal at the input. And that is given by this expression here, FKTB. Well, let's make B 1 hertz. Without really any loss of generality, we're going to make B 1 hertz. So what do you get? You get FKT over P0. That's the MDS. So if you look at this expression, you see what you have here. If P0 is equal to the MDS, you have 0 dB signal-to-noise ratio. As the P0 goes up, you're improving your signal-to-noise ratio. That's very important, because that signal-to-noise ratio can be improved two ways: increasing the input power or reducing the noise figure. They need to be considered collectively. You shouldn't focus on noise figure without input power. They need to be, I need to stress that. You need to consider both of those parameters together when you try and pick the right amplifier for your application. And if we just go through this a little bit, we can define an MDS at the output, which is just the gain times the MDS at the input. Do some manipulation, and you can find B0 at the output is just this term here. And then what people like to do is kind of extrapolate P out to the maximum and get a P sat and come up with this kind of rule of thumb. And I think it's confusing, and I think it's misrepresentative. So I don't really particularly care for it, but it's used regardless. Now, you can say, oh, well, I want an amplifier with high P sat. You kind of relate to that. As my input power goes up, I want to improve my signal-to-noise ratio. The higher P sat allows me to do that. Yes, necessary, but not sufficient. I want a low noise figure. Sure. Does noise figure trump P in? Again, I can balance that. You need to decide that. Was noise figure more important? If I'm doing a cascade analysis, I want my gain, for example, to be high. But according to this, I want to minimize my gain because I want to minimize my noise power at the output. So there are some contradictions between standard cascade analysis for designing for lowest noise figure versus designing for best noise output power. All right, and this is, again, in a white noise region. The other issue is that a lot of people use this in both flicker and white noise regions, and that's not correct. It doesn't apply in the flicker region. So minimize gain, okay, and noise figure, okay, maximize input power, okay. What you're going to find is that that's very difficult to achieve with a single device. And ultimately, devices will need to be cascaded. And there are implications when we cascade, which we'll study as we go through the presentation. So let's look at flicker noise. Again, we talked about it earlier. We know it's an upconversion process of the near DC or flicker noise of the amplifier, which gets parametrically up-converted to the carrier when a carrier is present. It has a property whereby it rolls off at 10 dB per decade or 1/f, which is why it's called flicker or 1/f noise. It's not unique to amplifiers. It's pretty much observable in most things in the world. People like to use the stock market as an example, right? It doesn't crash that often, so the number of occurrences is very low. But when it does, oh my goodness, it's a big deal. But yet every day it moves a little bit, and we get hundreds of fluctuations and a minute, and nobody really cares too much. So the impact of that is not too bad. That's analogous to a 1/f type process. So how is it generated? There are several theories. Two that are very commonly used have to do with the fluctuation of charge carriers due to surface effects, surface traps, and fluctuations in conductivity due to fluctuations in bulk mobility. So for example, this paper here, the authors derived an expression for the 1/f process using the Huga parameter, okay, using this methodology here, and they've defined an equation that accurately predicts the 1/f process for their device. Nothing wrong with that. The only issue is I guarantee you that maybe aside from the semiconductor physicist designing the process, most people don't know any of these parameters. Certainly the FET designer probably does not. And I can almost guarantee the amplifier designer doesn't really know any of these parameters. So unfortunately, that leads to a lot of experimental data needed to be taken. It's always nice to have an expression because then you can optimize your device for additive phase noise, but that doesn't ensure that that will be carried on through the design of the amplifier. And there are similar papers for HBTs or for bipolars. I've listed some, some rules of thumb that one sees for HBTs or bipolars, where you want a large device periphery and run that at a small quiescent current. You want to have a high unbypassed emitter resistance. Okay, so all of these things, we're going to look at some of these rules of thumb as we go through the presentation and see if we can validate some of them. The one thing we can say with amplifiers, that it's definitely dependent upon the DC current, the DC voltage, the device type. Am I a PHEMT? Am I an HBT? The process node size is extremely important. And with the PHEMT, you're talking about the gate length. Is it a 0.1 micron? Is it a 0.5 micron? With the bipolar process, you're talking about the base thickness and the emitter width. The power density, again, goes back to this. How much periphery do I have compared to the current I'm actually running through it? It results from fluctuations in the input and output impedances of the amplifier, which result in fluctuations in the insertion gain and phase. It can be affected by your input matching criteria. It's definitely a function of input power, right? We've seen that in the white noise region. And I'm going to go out kind of on a limb here and say it's a function of carrier frequency, but you'll see why as we go through the presentation. You'll often see that it's not a function of frequency, and oftentimes the performance is not. But because of some other things that you need to consider, you need to be at least conscious of what your carrier frequency is and the limitations that that carrier frequency may possess. We have a few blogs on the Mini Circuits website that deal with this. Okay, these are examples from two of those. Here we have a cross-section of a bipolar device, and you can see pretty clearly here that the collector emitter current, right, flows through the base. Here's our base. It's extremely thin, but there is some recombination and generation noise occurring, and that tends to increase the 1/f noise. So it's nice to make the base region very thin. With the PHEMT, we flow under the gate. So therefore, the 1/f noise is a function of the gate length. And it turns out as the gate length gets smaller, as is needed to operate higher in frequency, the trapping density increases. So you'll see that the 1/f noise tends to get worse for the smaller gate length PAMPs compared to the higher. And you can read these at your leisure. This is a paper from NASA that did a really nice job demonstrating some of those rules of thumb. So what you see here, you have 3 different peripheries. You have this, the 0.5 micron is the base thickness. Then you have the number of fingers and the gate, the emitter length, making up this term here, 0.5 times 1 micron, 2.5 microns, and 10 microns. And you can see as you increase the periphery for a given current, the 1/f improves. The power spectral density of the 1/f process improves as the periphery increases at a fixed current. On the other side, you see the same thing, and what happens as you increase the current, it gets worse. So those 2 rules of thumb, we've been able to validate through this paper here. This is interesting now, because what you're seeing here are examples of about 20 different mini circuits amplifiers. They're composed of PAMPs with the dashed lines and HBTs with the solid lines. Let's just look at the PAMPs for right now. What you're seeing here is the effect of reducing or increasing the gate length. These top ones go from 0.15 micron, 0.25 down to 0.5 micron. So it's clearly obvious from this that the higher, the larger, the longer gate length parts perform better from a 1/f perspective than the smaller gate length parts. Does noise figure come into this yet? Is that rule of thumb showing up in anything we see here? No, no. Have to be careful. Don't use, oh, I want the lowest noise figure, so I'm gonna pick a 0.15 micron part because I can get the lowest noise figure. Do you realize that you're killing the 1/f performance if you do that? If you can get away with a 0.5 micron part at a higher noise figure, integrate this curve. Integrate it like we showed earlier. Calculate the jitter and see how you do. Don't simply rely on noise figure as the sole parameter. The other thing is, maybe I have a 1 dB noise figure part that has a saturation output power of 0 dBm. That's going to limit my signal to noise ratio, right? You tend to see lower output powers at 1 dB compression, for example, with a 1 dB noise figure part than you may be with a 3 dB noise figure part. Noise figure and power have to be considered together. Now look at the HBTs. Look at the improvement in the 1/f noise. Even though these might have a higher noise figure, you can start to see some of the PAMPs are finally starting to get evidence that their white noise power is less than something from the HBT. But look where it starts. Again, integrate this and see what that gives you. Does this really matter for your application? Maybe it does. If you're concerned about very, very far out offset frequencies, sure, maybe you want to consider that. If you're not, if you're concerned about overall jitter and you need to consider the low offsets, you need to integrate this and figure out what's the best for you. Notice also that the HBTs are much more consistent. There's much less spread here in 1/f and white noise power density with the HBT process. These are all 2 micron emitter widths. And everything here you see here are examples that operate from DC to 27 gigahertz. It's a pretty wide range for a single emitter width, where here we need to go from 0.15 to 0.5 to cover from roughly 50 megahertz to 45 gigahertz. So don't pick a high frequency part with a very small gate length if you're concerned about 1/f noise. So let's go make some measurements now. And one of the things we want to ask is, well, we said low power, high power. How do I know what's low power and what's high power? Well, we're going to use this equation as a reference for it to make that decision for us. We're going to start by reducing the P0. okay, the input power, and we're going to look at the white noise power spectral density. And when it's flat like this, you know you're pretty much white noise limited. And you're going to back calculate the noise figure from a measurement of the additive phase noise in the white noise region, knowing the P in. I've got to know two things very, very accurately: the P in and the additive phase noise. Once I do that, I calculate my noise figure, and one will find that as you go low enough in power, your noise figure, as calculated from this equation, will agree with the noise figure you measure with a noise diode setup. Once that occurs, once you have good agreement between those two, you're in small signal. You don't have to go any lower. You can start increasing your signal power above that to see what happens now to try and maximize that signal to noise ratio now. So once you've identified, all right, I'm small signal, then you start increasing the input power and look at the effect of improving your signal to noise ratio. Oh boy, we're going to talk about this in a minute, which again goes back to why I said earlier, you got to be concerned about carrier frequency to some extent, because these are different carrier frequencies. And why are they so different? All right, if you're making a measurement at 2 gigahertz, I get this. If I'm making it at 7 gigahertz, I get that. It's not, you'll see, it's not the amplifier. It's coming from the test set, which is why you need to be mindful of what your carrier frequency is. So how high is high power? Again, we want to continue to increase the input power, maximize the signal to noise ratio, but how high can I go? Well, what we do is we say, well, what can my test set support? Right? I can't get any better signal to noise ratio than my test set can support. And notice this is identical. That didn't change. So now I'm passing through, I replaced the DUT with a through, and I'm making that measurement, and I see the same thing. So it's obviously not DUT related. Kind of good to have that data so you can show the customer or the user that, well, it's not the amplifier, it's just a limitation I have. We have to just accept it at this point. And you also see some other interesting features on this curve. You see this increase in additive phase noise once we go above a certain offset frequency. Why? What's that all about? These analyzers suffer from an effect called decorrelation. It's a function to some extent of the total phase length from the output of the instrument back to the input of the instrument. So you want to try and minimize that. That's why we said earlier, use short, well-matched, phase-stable RF cables and keep them as short as you can. The newer analyzers that are starting to come out now have provisions to account and to mitigate this effect. But with this vintage, it's here. We understand it. We have to deal with it. Then in the middle, you get kind of a mix of a little bit of everything, right? You don't know quite what's going on in the middle here. We've got these deep nulls. We've got some peaking. How come these are higher than here? What's going on here? R&S will say that if your minus 177 is the thermal noise power of the phase fluctuations, okay, plus 13 is my input power. So that dBc is minus 190 for this case. If I'm above that, they will say, well, it's a legitimate measurement. So you can see here, we're kind of about 185. We're getting very close to that number. But what we don't know is, would this continue? And it's going up because of decorrelation. We can't find this point. And that's the reason why the decorrelation perturbs the measurement here. At the higher carrier frequencies, you can see for the same source level, we're well above that. So it's not thermal noise limited. It's limited by other effects, but it's not limited by the minus 177 and the plus 13. But you also see the decorrelation showing up there as well. But then in the middle, again, you see kind of a mix of different effects. And it could be, doesn't have to be, but it could be related to something called cross-spectral collapse. And there's a nice paper here that gives specific examples of some of the shapes you can get when you control what the the AM leakage into your mixers in your phase detector, if you can control the amplitude and phase of that leakage in such a way, you can show that these type shapes are inevitable. And even if you go to the Roden-Schwartz app note, you'll see that they feel that AM distortion, again, AM leakage coming into the mixers, mixing with the desired, depending upon the phase relationships, can produce results that look like this. And you just have to be aware of it. There are some things you can do, not a lot you can do, but if you all of a sudden get a measurement that's, minus 200 dBc per hertz, there's probably something wrong with that. Power supply noise can also cause a similar effect. It can leak into, mix with the desired outputs of the mixers and create similar types of distortion. So you just need to be aware of it. Not a lot you can do about it, but you should at least be aware of it. So this is going to be an example of measuring one of our amplifiers. This happens to be an HBT part, the LVA 273PN Plus. As you'll see momentarily, it's a distributed amplifier. It's a distributed HBT amplifier. And this pattern of increasing input power at a fixed carrier frequency of 2 gigahertz, mimics this curve very well. You'll notice that in the 1/F region, right, B-1, it doesn't change. I'm changing my input power and therefore my output power, and I'm seeing the increase in input power resulting in an improvement in my signal-to-noise ratio in the white noise region. But this does not change, right? That B-1 does not change. So this is just experimental confirmation that this curve is extremely accurate. So this, again, is technically small signal operation. So I'm going to continue to increase my input power. But we all know at some point, that's going to stop. At some point, I'm going to compress. I'm going to reach saturate. I can't go indefinitely. So something has to change as I continue to increase my input power. And that brings us into the large signal region. I'm going to switch parts, also in HBT, different topology. This is a Darlington Cascade, but it demonstrates this large signal behavior over power levels that I happen to be able to apply readily during this measurement. So what we've done is we've done exactly as before. We've increased the input power. We've watched the signal-to-noise ratio improve. Those are these curves here. But then at some point, as I continue to increase input power, look what happens. Everything starts to degrade in both flicker and white. That's not predicted by the small signal theory. That's a large signal effect, and that's why you need to, when I said earlier, you got to be very careful. You got this expensive, extremely low phase noise oscillator, and you're driving an amplifier at the wrong power level, and you're degrading its performance significantly, and you don't know why. Why am I getting this? What's going on? You're driving that amplifier to a point where it's becoming nonlinear, and that affects both the white and the flicker noise. What causes that? We're going to go into that as we go a little bit further. So one of the things that you want to do when you're characterizing your amplifiers is, again, start in the small signal region. Notice how this is noise figure as calculated from this formula versus input power. So again, see how these curves start to flatten out? Once those curves are flat, that is equivalent to what you would measure for noise figure using a noise diode. You start increasing the power from there, but look what happens. The noise figure does not stay constant. And I'm going to ask, how many are actually taking this into account in their cascade analysis? That as you drive the amplifier further from small signal, your noise figure is increasing. That's something to think about. Because if you have requirements for, say, out-of-band noise, like in SATCOM, transmit noise in receive band, and you assume that your noise power is constant with output power, and then you find out that, gee, I'm marginal. Why am I marginal with my because you didn't take into account the fact that as you drive any amplifiers after the oscillator into compression, or just harder than you would think from a small signal standpoint, you're going to be increasing your noise figure. So that's one thing. The other thing is look at these slopes. This is 1 dB per dB. So in other words, if I increase the input power by 1 dB and my noise figure goes up by 1 dB, I have not degraded my signal to noise ratio. So 1 dB per dB, I'm constant, I'm flat, I'm not changing my signal to noise ratio. If this slope changes and becomes greater than 1:1, then my noise figure is increasing greater for the 1 dB increase in input power. So I'm degrading my signal to noise ratio. So as these slopes, as you can see here, this is almost 2:1 compared to the LVA part, which is still increasing, but the signal to noise ratio is constantly improving because I never exceed 1 dB per dB. So plotting noise figure from this formula versus input power is very insightful. And it gives you an idea where you can operate. Now, why at this point does this slope start to change? That's what we need to ask. Why is that happening here? This is going to happen with every amplifier. Okay, let's face it. It's not unique to the GVA. It's just where does that occur and why? And to get a little better insight into that, we're going to look at some AM to PM distortion in just a little bit. So again, if we plot additive phase noise at two specific offset frequencies as a function of input power, you get these nice shapes. This is a nice way to look at additive phase noise at two specific offsets, flicker and white, as a function of input power. And wow, look at that inflection point that we see with the GVA. And notice at this power level, +1, 18 plus 19, I'm not even compressed. So again, I'll get a high P SAT amplifier and it'll be great. I don't know about that, all right? There's something else going on here. Maybe P1 dB is necessary, but it absolutely is not sufficient based on this argument. Why does this part continue to improve as it should? Well, there's obviously a difference between these two parts. Is it that this is distributed and this is a Darlington cascade? It could be. In fact, distributed amplifiers are known to be similar to like parallel combining, which we'll see later, does present some type of an advantage, but I don't know that from here. But there's something going on between these two, and we need to understand why. What is causing this? So let's try a different part. We're going to try a similar part. So now we're going to try, again, a Darlington with emitter resistor feedback versus a Darlington cascade. They both have emitter resistor feedback, but one has much more than the other. And look at the differences now between these parts. This, in the white noise region, he arguably hasn't even changed yet a little bit. You see a slight bit of degradation occurring in the flicker noise region, but still much better than this part. So well, they're kind of Darlingtons, they're similar. So again, it's something else. What else is going on? What could be causing this? Again, does this rule of thumb help me here? No, it really does not help me here because I've got very similar RF parameters. And that's the frustrating part. It's really not sufficient to try and guess how my phase noise performance is going to be at a specific input power just based on standard RF criteria, gain, P1 dB, noise figure. A lot of these things just need to be measured. So let's take a closer look at the GVA 84 versus the GVA 62. And here you start to see some agreement with some of those rules of thumb. You may not be able to do this for every amplifier because if an amplifier has DC blocks, you obviously can't measure the gain at DC. But a lot of the HBT designs do not. So one of the things you want to do is compare the gain at DC. And we said lower gain, Kind of helps. Okay, well here we're seeing agreement that, hey, lower gain, that's pretty significant. The other parameters are fairly consistent. So you don't get a lot out of that. But this should be one indication that maybe I want to look at this part because I see my DC gain is lower. If you need higher gain, maybe you have to cascade rather than go to a higher gain part. That's a decision you need to make, and we'll see how to better make that decision later on. But what's not obvious, and again, you would never see this. I'm kind of sharing some information here that's not typically available, but the emitter feedback here is fairly large. You can just look at the scale versus the emitter feedback here. So that emitter degeneration, adding the emitter resistance does obviously help. But again, as a user of an amplifier, you're getting RF parameters which really are not going to help you, with the possible exception of look at the gain at DC. So to help understand the why does this inflection point occur, we're going to look at AM to PM distortion. It's almost never specified. You typically have to measure it yourself. This describes how we measure it. Use a vector network analyzer at a constant frequency and you sweep input power. Here we're going from -10 to +10 dBm at a fixed carrier or a fixed frequency of 2 gigahertz in this case. This obviously needs to be done as a function of carrier frequency, but here we're just looking at 2 gigahertz. And here's P in versus P in, nice straight line. Here's P out versus P in. We have gain versus P in, AM to AM, and phase versus P in. And what we'll do to generate AM to PM in units of degree per dB, we take a 1 dB window and we calculate the slope of the phase curve over that 1 dB window, and we plot that point. Then we move the window by the delta of the frequency of the power delta, and we continue that process throughout the entire input power range. And you start to get these very unique and very consistent curves. They occur at a specific power level and they have a peak, okay? This one, as you can see, for the LVA is a little bit lower than the GVA, but these are the kind of curves you want to generate, and you want to try and say, all right, can I correlate AM to PM versus additive phase noise? And there is correlation. Okay, so AM distortion will generate phase distortion. When you compress, you're generating amplitude distortion, which creates the phase distortion. So we want to see, is that AM to PM distortion influencing our additive phase noise measurement? So here's all three parts. And again, if you look at the RF parameters, they're not that different. Certainly not enough where one could say, oh yeah, it's obvious to me that the GVA 84 is going to have an inflection point. It's impossible to make that assumption based on RF parameters here. So if you look at good, best, and better, you can see for the LVA 273, we run the saturation, it doesn't care. Partially due to the fact that its AM to PM distortion is extremely low. So when you have low enough AM to PM, you won't even see these effects. And I bet a lot of people miss that just because they happen to be operating at a frequency where the AM to PM distortion is very good, and this entire effect is unknown to them because they're not observing it. But you change the amplifier and all of a sudden you could see it. So it is something that should be measured if you're interested in low additive phase noise. When you measure your standard cascade parameters, you should think about adding AM to PM. If we look at the 62, notice I can run almost at 1 dB compression before I start to see something happening here. For the GVA 84, I'm barely a quarter dB compressed at that inflection point. So again, that rule of thumb is not looking too good, right? I've got a high P sat here, I've got a high P1, I've got the highest really P1 dB, yet that inflection point occurs well below anything to do with that 1 dB compression point. And the GVA 62 is a little bit better. It's about 1 dB, 0.25, and this guy is saturated. So there's a paper that you can reference, which goes into this in a little bit more detail, but you can see the shaping that they report on is exactly what we have here. So there is correlation. It's not perfect, but you need to be aware of it. It's not like, oh yeah, if I have 1 degree per dB, I'll be perfect. Maybe. If I have 5, I'll be terrible. Well, maybe not. You know, these are about the same, yet I can operate this guy further into compression than this. That's because the resistive feedback, the collector resistor and the emitter resistor are helping me linearize that amplifier. Does it change with carrier frequency? Of course. Of course it's going to change with carrier. Is it consistent? Of course not. So again, something that just adds to the frustration. So if you look at the LVA, for example, it gets worse with increasing carrier frequency. All right, not a lot, but it does get worse, okay? If you look at the Darlingtons, it's worse at the lower frequencies, and it gets better as you go up in frequency, which is why if you happen to be operating at a carrier frequency where the AMP is low enough, you're like, Joe, I don't know what you're talking about. I don't see any of this stuff, all right, because you got lucky, all right? Operate at 100 megahertz for this guy and see what happens, okay? It needs to be known. And again, it just adds to the frustration because nothing is consistent, and it just does require a lot of measurements being made. And again, if you look at these parts, they're not that different from an RF standpoint. If you look at the output powers, the P out at 5 dBm, at 10 dBm, at 1 dBm, they're not that different. Yet I see radically different performance in additive phase noise. So let's do a case study. Let's look at our favorite LVA 273. Here we're looking at different carrier frequencies from 2 gigahertz up to 8. Notice that the compression curves are very consistent, but the AM to PM curves are not. Another indication that maybe P1 dB, again, maybe it's necessary, but it's absolutely not sufficient because one would not anticipate for the same level of compression that I go from 0.5 to 2.1 degrees per dB over carrier frequency, given that they're operating at essentially the same level of compression. So again, I'm going to plot this a little bit differently. We're going to look at the 10 kilohertz offset and the 100 kilohertz offset versus input power at different carrier frequencies. And notice at 2 gigahertz, you see how it kind of flattens out? That's that, well, 1 dB per dB. I'm not degrading, I'm not improving my signal to noise ratio, but I'm not degrading. And it maintains that well into saturation. Not all amplifiers, as we'll see, like to be operated in saturation, but at this frequency, this part is okay with it. But look at some of the other carrier frequencies. Look what happens as you start to approach where that peak in AM to PM occurs. You start to see the degradation occurring in your additive phase noise at both offsets as you start to move into the region of the peaking in the AM to PM, which is why it's important to understand where does that peak occur, well, number one, but again, how close to that peak can I operate in input power? And what if I operate on the other side of that peak, where it seems to come down again? So those are two things we want to ask. What's better, operating on the input side, input and output? Those are questions that you have to answer. And we'll show you some measurements later on where we go into that. Where should we be operating this amplifier given this AM to PM characteristically shaped curve? And again, adding more to the frustration, here are two very similar parts. You have two distributed HBT amplifiers. Variants, one is a variant of the other. One is actually a higher power, slightly higher gain version of the other. You would think, oh, these should be very similar. Maybe this one should be better because it's got a higher P1 dB. Well, look at the AM to PM. It doesn't follow. Okay, it's not following the increase in compression. Like if we put 0 in here, 17 dB gain, I get out 17, that's the compression point. All right, so So in this vicinity, you're operating over here in the vicinity of 1 dB compression. It's the same thing here. If I put in +1, 19, I get 20. I'm operating. So both of these operating ranges are similar. We're operating in the vicinity of the 1 dB compression point, but we're getting extremely different AM to PM distortion behavior. Why? All right, we're going to continue to investigate that. Is there something I can do knowing this? What about temperature? Of course, right? Luckily for temperature, we can say the AM to PM curves follow the gain. So as the gain goes up as you go cold, for example, the P will go down. So that you can kind of anticipate just by measuring the gain variation at different frequencies, at different carriers over temperature. And you may say that, all right, well, you know what, I'm okay at 0 here, but I may need to back that off a little bit to get the same amount of distortion over temperature. But that you can make a reasonable assumption just based on measuring the gain variation. What else can we do? Is there anything else we can do? Well, one of the only knobs we have really on these amplifiers is the voltage and current. Now in this particular part, we have, this is now the 6183, the higher power variant of the LVA 273. And with this part, the only controlling knob I really have is the draining voltage. Excuse me, the emitter voltage is an HPT. So I can adjust that. As long as I stay within the absolute max ratings, I wouldn't go to the absolute max. You got to be a little bit careful, but if there's a range, you can certainly experiment within a range of device operating voltages. And does that have any effect? Well, what we did here is we picked an input power, in this case, plus 5 dBm. So we're here with AM to PM distortion, and we plotted it at different voltages. So 6, 7, 8, and 9. So you can see as you go up in voltage, the curves move out. So we get a reduction in AM to PM distortion as we go up in voltage. Does that translate to an improvement in additive phase noise? Well, let's see. So here is what happens when you go from 6, 7, 8, 9. So you definitely see an improvement occurring at this input power in additive phase noise if I change my device voltage. You're going to have to figure this out on your own, though. The manufacturer's not going to tell you this, right? They pick a device operating voltage for best overall performance, HTOL, all kinds of things. So they're not going to tell you, oh, yeah, raise it by a volt and it'll work. They don't know that for the most part. You're going to have to measure this. So in this case, if we choose to operate here, we can pretty much get back to a pretty good number. You know, 171 at 100 kilohertz. That's a very nice number. Where here it was 166, 167 maybe. So I got an improvement running in a larger signal region by just changing the device operating voltage. Well, what if we pick a different power? What if we right at the peak? What can I do here? Can I regain that performance if I'm operating at the peak? So we do the same thing. We vary the voltages from 6 to 9, and yeah, you can see there's an improvement. Here I would have to go to 9 volts, and I see an improvement. But notice though, 168, 169 versus 171. I can't get back to this, but I can improve. Okay, so here's some sort of indication that yes, you can maybe operate saturated, but you get some decent performance, but it may not be equal to what you can get operating on the lower input power side of that AM to PM curve. So we're going to look at cascading some amplifiers. Now, and again, this is not meant to be a general discussion of cascade analysis, but we're going to go through some examples that I think are insightful and would designed to just encourage you to make some experimentation before you pick a chain of say, for example, LO amplifiers. How should I best design this, and what should I consider when I say need to design an LO amplifier chain where I know I'm going to be running compressed or saturated. So we're going to look at 2 amplifiers in series first, and then 4 amplifiers in parallel. And why are we doing this? So now we're going to look at these other 2 sets of curves by Professor Rubiola. And we're going to look at what happens in the 1/F and the white noise regions. Now, when you cascade amplifiers, we all know what happens to noise figure, right? They have the cascade noise figure formula, which says it's the noise figure of the first, followed by the noise figure of the second, scaled by the gain of the first, et cetera, et cetera. We presented that equation earlier. So that's why you see a slight increase in the power spectral density in the white noise region. That's coming from the cascade noise figure effects. In the flicker noise region, though, you see a 3 dB degradation in your 1/F noise as you cascade. Why? Well, if you think about it, you have a perfect tone, no absolute phase noise, going into the first amplifier. Its 1/F noise will get parametrically upconverted to that carrier. That signal is then input to the second, where its 1/F noise will be parametrically upconverted to that signal. Those noise powers in those sidebands add as power. They add as a 10 log effect. The 10 log effect is what gives you the 3 dB. So when you cascade, you'll get the plus 3 dB log base 2 of M, where M is the number of stages. It's because the noise sidebands are adding using power addition. Okay, now we go to a parallel arrangement of amplifiers. And for this analysis, we're showing obviously lossless splitters and combiners. So you see there's no change in noise figure here. Noise figure is the noise figure of the amplifier. But why does this go down? Why is this improving by 3 dB? Well, again, think about it. You take your tone, it splits equally. Each of these tones is now going to have the flicker noise from each amplifier upconverted onto it. Right, now I've got sidebands. Then I come into the combiner. Well, the signal combines coherently using 20 log addition. The noise combines using power, using 10 log addition. So you have an inherent 3 dB advantage right there. That's what this is showing. The minus 3 dB log base 2 of M is when you run amplifiers in parallel. And that's coherent versus non-coherent addition at the output. So here's some case studies that we're going to do, again, mostly as examples, not meant to be an exhaustive study of cascade analysis. But here we do basically what we just said. We're going to cascade 2 amplifiers. I'm just going to put one next to the other and be happy with myself. I'm going to make some calculations of the small signal noise figure and gain at these 2 different carrier frequencies with no padding in between these. And we're going to show an example where I introduce a pad now between the 2 amplifiers. Why am I doing that? Why am I doing this? I'm doing it because I want to show that where I'm operating the first stage compared to where I'm operating the second stage. So if you look at the first stage, we're going from -5 to 5. If I look on this curve, I'm right about here. So I'm on the low power side of the AM to PM peak. I look at the second stage, geez, I'm over here. I'm saturated. Okay. If I look at the second case, I put a 6 dB pad. So what did I do? I brought that second stage 6 dB out of saturation. So now we have the same input power for the first stage, but now the second stage is 5 to 14. So it's coming to 5, and then the second stage starts here and goes into this region. So we're kind of right in the peak. You know, right in the peak. One is before the peak and one is to just before and right into the peak. So how would these compare? Well, let's see. Here we have the 0 dB case at 2 gigahertz and at 6 gigahertz versus the 6 dB pad in between the two. And it's subtle, but it's pretty clear that there is an improvement, right? If these curves, these arrows point to corresponding points on the one case versus the other, you can see that there's there's some benefit, okay? There's some benefit here if I pick the right power level where I can improve my performance simply by controlling where one stage is being operated. Now, again, I'm still running him pretty hot, all right? He's still pretty much compressed and saturated. But even with that, there's an improvement. But this is very subtle and it has to be measured. The other thing you'll notice is that, well, if I want the best performance at 2 gigahertz, maybe I'm going to run it +5. That's this curve. But if I want the best performance at 6 gigahertz, maybe I want to run here, which is like -1. So if I have a fixed power synthesizer that's running from 2 to 6 gigahertz, outputting +10, I need to get +5 at 2 gigahertz. I need to get -1 at 6. That means I'm going to put a pad and a slope equalizer. But you got to be very careful putting equalizers after synthesizers. You don't want anything that reflects power back into that synthesizer. So turns out a cascade of reflectionless filters provides a negative going slope that one would say get from any conventional reflective low-pass filter. But with these reflectionless filters, the return loss stays better than 15 dB. So you're not reflecting that power back into the oscillator, you're absorbing it within the filter. So I'm a big fan of reflectionless filters in chains that follow a low phase noise oscillator. If we look at a single stage now, versus the cascades. So we'll look at a single stage versus the best case in the cascade. And now you start to see the degradation associated with cascading stages in series. You can see now, wow, pretty much across the board, I see a degradation. I can mitigate it, I can minimize it by careful choice of operating point. But you can see we're fairly consistent with that 3 dB degradation that I expect. Now let's look at 4 in parallel, right? According to the theory, I should be seeing a 6 dB improvement. And I put 4 amplifiers in parallel. And again, where are we running these? From about 0 to +10. So we're pretty much going right through the peak at the input to here, but -6 to 5 at the amplifier. So we're pretty much consistent with the input power range we just did for the single stage and the 2 cascaded. We're running basically on the front end of that curve. So one would expect a 6 dB improvement. What do we see? I'm not seeing it. Why aren't I seeing it? Because I can't measure any lower than this. Unfortunately, it's my limitation of my test equipment. I can't demonstrate the improvement associated with running 4 devices in parallel. It's not that it doesn't work. I'm stuck at my noise level. So how can I demonstrate that this is actually an improvement? Well, what if we have a series, 1 driving 4? That's a cascade. All right. I cascade 2 things, they should degrade. But wait a minute, my second stage should have an improvement. So if I improve by 6 dB and degrade by 3, I should see an overall improvement when I cascade. So let's see, maybe this will now allow me to identify true performance rather than my noise floor. So again, similarly, we're going to start with a single stage. We're going to have a variable pad here. In this case, it's 0 dB. I'm going to drive off 4. And again, you do the small signal analysis. I get 8.1 dB noise figure, 33 dB gain. The noise figure improves with this part, with the LVA. Inside the ZX60 is the LVA 273. I should have mentioned that. So it's the same part we've been studying, just now in a connectorized version. And the noise figure improves at 6 compared to 2. So these are the small signal parameters. And again, we're going to be running now into the first stage, 0 to 10. So in this case, we're going pretty much through the full range of AM to PM distortion. We amplify. In this case, there's 0 dB padding. We come out of the splitter at this range, and then we go combine again and get this. So we're coming in here at plus 10. We're getting out almost a watt here at 6 gigahertz. And again, the second stage is saturated. All right, P into the first goes from small signal to large signal, right through it. The second stage is basically saturated. So similar operating points to what we did earlier. Then we're going to do, similarly, a case where we put an 8 dB pad, for example, in between the first stage and the times 4. We're also going to change up the input power range a little bit here. We're going from -6 to 5. So again, small signal to, again, just the front end of this curve. We're going to amplify, we're going to attenuate, and then we're going to go through the amplify, attenuate, and split, and come into the second stage at these power, again, -2 to 5. So both of these amplifiers now are running at the low power side. We combine them, I get 26 dBm out in this case. So let's see what happens. Now this slide is kind of a little busy, but it tells a nice story. First, we're going to look at the 0 dB case versus the 8. And it's pretty obvious that in almost all cases, bringing that second stage out of deep saturation results in some improvement. So it kind of says we want to run on the front end side of that AM to PM distortion curve here. And we're not really taking much of a hit in performance going from 0 to 8 dB. The noise figure doesn't increase that much, as you saw. The gain obviously goes down, but do we care? Well, we knew that. We put a pad in. So if we look at this case here, this represents the best in terms of additive phase noise performance. So here at 4.5, 5.8, again, front end of that curve, we're getting out plus 26 dBm. So, well, that's not enough. I need more power. So I'm going to look at this case, and I'm going to run it to say, oh, now I'm going to get a watt. Well, let's calculate our noise figure like we said we should be doing when we do this cascade analysis. Look what I'm doing to my large signal gain. I'm hugely saturated here. I'm only 3 dB compressed here. I'm almost 13 dB compressed here. Look at my noise figure. 4 dB went to almost 21 dB noise figure. You got to take that into account, because that out-of-band noise is going to be 20 dB higher than you expected. So no big deal. I'll just back off my input power. All right, so I go from here to here. Look at that. I get more gain, and I get about the same noise figure, and I still get more output power. Yeah, but I never recovered my additive phase noise to the same extent. I'm still worse in this case than I am in this case. What am I giving up? I'm giving up about almost 3 dB in output power, but that's a trade-off that you have to make. Maybe there's a different configuration we can run. So the point is here, it's not just, I'm going to cascade identical stages. There are different configurations that need to be considered and power ranges into each amplifier that need to be considered. And tracking those power ranges against the AM to PM distortion gives you a good starting point and a good place to design from. That's why we spend a lot of time discussing it and going through these examples. If we look, again, this was 0 dB versus 8 dB. Now we're going to look at 0 dB versus 8 dB at 6 gigahertz, and then 8 dB versus the best case we got out of the 2 in cascade. Now I'm going to start to see, is cascading in parallel offering me an advantage? So one thing we see here, yeah, you know what? Controlling those input power ranges, I can achieve better performance. Those power ranges are going to largely be dictated by where they lie on that AM to PM distortion curve. Well, how did this, the best case here compared to the best case here. And you can see over a lot of that range, these curves are all higher than here. So I'm starting to see the advantage of paralleling versus just cascading here. Cascading a single with 4 in parallel versus 1 and 1. Again, best case versus best case. Look, there's a significant advantage here. So this is now we're starting to see or start to demonstrate the performance you could obtain by paralleling amplifiers. Before we were noise floor limited, we couldn't see it. If we do this at 2 gigahertz, it's even more, a little bit more obvious. So we're comparing worst case versus worst, and worst case versus best here. And worst versus best, there's still an advantage. So kind of independent of carrier frequency, this technique holds. And again, something that it's not simple formula, just do this. You need to experiment, find the right padding, the right input power ranges, and the power you get is going to be the power you get. All right, if I have to set the input powers, I can combine, I get that power. If I need more, then I may have to violate the best input power conditions, and I'm going to sacrifice my additive phase noise to some extent. And you need to decide if that trade-off is worthwhile for your application. So that's the end. We have a bunch of references here that you can look at. You can always email me if you can't read these, and I'll be happy to send them out. And we also have some webinars already published on the same topic, but this one is a little bit more comprehensive and showed a little bit more details that weren't available at the time the other webinars were released. So I encourage you to go look at this, come back with any questions through our applications team or email me. And again, thank you very much for your attention. Hope you enjoyed it.